Of all the mysteries that the human brain presents, perhaps one stands above the rest. How does it learn so effectively? In the world of artificial intelligence, scientists and engineers have spent decades trying to replicate the brain's learning mechanisms. Their efforts led to backpropagation with gradient descent, the workhorse algorithm that powers virtually the entire field of machine learning today. Due to its remarkable success, researchers began to speculate that perhaps brains do something similar. However, there is a fundamental problem. The backpropagation algorithm contradicts essential biological principles of brain function, making its exact implementation in neural tissue virtually impossible. In recent years, however, an alternative algorithm called predictive coding has emerged that is not only more aligned with the brain's biological hardware, but sometimes can work even better than the backpropagation itself. In this video, we will build predictive coding from first principles, explore what issues of biological plausibility it addresses, and how it might inspire the next revolution in machine learning. The fundamental challenge that computational systems must solve is called credit assignment. When you have a system with numerous parameters, like connection weights between neurons that can be adjusted to achieve a desired output, such as recognizing objects in an image or executing appropriate actions, how do you determine which parameters to adjust and by how much? Artificial neural networks solve this elegantly through what's called automatic differentiation. Because the entire computation can be represented as a mathematical function, computers use calculus, particularly the chain rule of derivatives, to calculate precisely how each parameter should be nudged to guarantee improvement in performance. If you're interested in a deep step-by-step derivation of how backpropagation works, I've covered this in one of my earlier videos. However, despite its remarkable success in machine learning, evidence suggests that the brain almost certainly uses a different approach. There are various reasons why backpropagation doesn't map directly onto neural hardware, but luckily, most of them have biologically plausible workarounds. What is crucial for our discussion today, and why I'm extremely excited about predictive coding, is that it addresses two fundamental constraints that are absolutely incompatible with neurophysiology, and which are the biggest reasons why brains cannot perform backprop, namely lack of local autonomy and discontinuous processing. Sounds confusing, so let's unpack what this means. Artificial networks operate in strictly separated phases that alternate sequentially. First, information flows forward. Input propagates across layers to the output, generating a prediction. Next, this prediction is compared against the desired outcome, calculating an error. Then comes the crucial backward pass. This error travels back through the network layer by layer, determining precisely how each weight should change to reduce future errors. Finally, all weights update simultaneously, and the cycle repeats with a new training example. For this process to work, neurons must essentially freeze their feed-forward activity values, like taking snapshots of activity and holding on to them while error signals flow backward. But our brains don't work like this. They don't hit pause between thinking and learning. Communication in biological tissue is relatively slow compared to silicon processors. If the brain followed backpropagation approach, it would have to completely stop information processing for hundreds of milliseconds before performing the backward pass to update connections. Imagine experiencing brief blackouts every time you learn something new. Instead, biological brains process information and learn simultaneously in a continuous stream. There is no evidence for separate forward and backward phases. Neurons receive, process, and adapt to information in parallel, without pausing computation to accommodate learning. The second major issue with backpropagation is its reliance on global coordination. Not only must there exist some kind of central controller to switch the entire network between forward and backward modes, but this information must propagate in a precise temporal sequence. Even if neurons could somehow freeze their activity, they would need to unfreeze in strict succession. You cannot compute errors for a given neuron before its downstream partners have finished calculating their own errors. Everything we know about brain physiology suggests that such global coordination is extremely unlikely to exist. While there are some coordinating mechanisms, oscillations like theta and gamma rhythms, attentional systems, and neuromodulators like dopamine that influence broad populations, these mechanisms operate at much coarser temporal and spatial scales than would be required for backpropagation, which relies on cell-by-cell precision. Instead, individual neurons and synapses mostly function as autonomous agents, modifying their states based solely on information physically available at their specific locations. The brain operates in a massively parallel, locally autonomous system, where computation and learning occur simultaneously throughout the network in a distributed manner, without centralized control. Now that we understand the limitations of backpropagation in biological systems, let's explore a promising alternative: the predictive coding algorithm. This framework originated from mid-20th century research, proposing that the brain's fundamental objective is to predict incoming sensory information. From an evolutionary perspective, prediction enhances survival by allowing organisms to anticipate threats and interpret noisy observations. There is also an efficiency argument. Neural activity demands considerable metabolic energy, and a brain that can predict incoming signals only needs to process unexpected information, reducing the metabolic burden of transmitting predictable and thus redundant data. In this view, the brain's primary task isn't simply processing incoming stimuli, but constructing an internal model that explains sensory inputs. When this model predicts accurately, minimal additional processing is required. When predictions fail, the resulting prediction errors signal that the internal model needs updating. Predictive coding formalizes this concept as a hierarchical system, where each neural layer attempts to predict the activity of the layer below it. The lowest level corresponds to raw sensory input, like pixels of an image, while higher levels encode increasingly abstract features and categories that enable effective prediction of the lower-level visual features. Although real brains possess more complex connectivity, including associative connections between different modalities, the simplified hierarchical model captures the core principles. Information flows bidirectionally through this hierarchy. Top-down connections carry predictions from higher levels to lower levels, while bottom-up connections carry prediction errors, differences between predictions and the actual activity. This abstract description of information flow will guide our derivation of how individual neurons must interconnect. We'll approach our network as a so-called energy-based model. Essentially, this means associating each possible network state with a single number, representing some form of abstract energy. We can then derive rules for how the system should evolve to reduce this energy. This framework parallels physical systems that naturally progress towards minimum energy states, like a ball rolling downhill to minimize gravitational potential energy, or proteins folding to minimize atomic interaction energy. Since the brain is also a physical system, it too evolves towards states that minimize some form of energy. In predictive coding networks, this energy relates to the total magnitude of errors between predictions and reality. To visualize it, consider the following analogy. Imagine the network as an assembly of movable parts, springs and connection rods, where each neuron is a node sliding on a post, its height representing its activity level. On the same post slides a platform corresponding to its predicted activity, determined by the neurons from the layer above. A spring connects the neuron node and the platform, and the tension of the spring, proportional to its squared length, contributes to the overall energy. If the neuron's activity deviates significantly from its predicted value in either direction, the energy increases. A neuron's activity can be freely adjusted, while its predicted activity is determined by other neurons. We can visualize it as rods connecting neuron nodes on the layer above to the platforms at a current level, positioned at variable angles corresponding to synaptic weights, which determine how other neurons' activities influence the prediction. the sum of activities from all neurons in the layer above multiplied by synaptic weights connecting them. Note that typically activities pass through a nonlinear activation function, like sigmoid or ReLU, but I'm omitting it here for simplicity. The prediction error for each neuron, then, is the difference between its actual and predicted activity. And the total energy, representing the overall tension of all springs, sums the squared errors across all neurons in each layer. The network's fundamental objective is to minimize the total prediction error by finding the optimal configuration of neural activities and connection weights. As we'll see shortly, when presented with training examples, the network settles into states that balance these elements to represent input-output relationships as accurately as possible. So let's determine precisely how neural activities and connection weights should adjust to reduce this total energy. The resulting mechanisms will align surprisingly well with known neurophysiology. During the system's evolution, it effectively rolls downhill on the energy surface, defined in a high-dimensional space, where each coordinate represents a parameter, such as neural activity or synaptic weight. Mathematically, this downhill roll corresponds to moving in the direction of steepest descent, opposite to what's called the gradient of the function, where the gradient vector points in the direction of steepest ascent and is composed of derivatives with respect to each parameter. Let's isolate a specific neuron at layer L and determine how to adjust its activity to lower the energy. To find this derivative, let's revisit our energy definition, where we sum over all posts and add up the squared lengths of all springs. Since the derivative of a sum equals the sum of the derivatives, we can examine each post individually and ask, if we slightly adjust the node height x sub I at layer L, how would the tension at any post change? Then, we add up all these effects. First of all, notice that this neuron doesn't affect the tension at any spring at layers upstream from L, so the derivative of all those terms is 0. Even within layer L itself, the only spring directly affected is the one connecting neuron I to its predicted value. By differentiating the square of the prediction error, we find that the rate of change of this neuron's activity is the negative of its prediction error. This makes intuitive sense. When the error epsilon is positive, meaning the neuron's activity exceeds its prediction, the spring wants to contract and pull the value down towards the prediction, creating the negative rate of change. Conversely, if the value is lower than predicted, the spring tension drives the neuron's activity upward. But there is additional complexity to consider. When we adjust the height of the node at layer L, beyond affecting its own spring, it also influences the predicted activities at the layer below it. To compute the complete derivative, we must account for how changing x sub I affects these downstream errors. Recall that the predicted activity of a neuron is given by the weighted sum of activities of upstream neurons. So when we change x sub I at layer L, for each neuron at the layer below, it affects the predicted value proportionally to the weight connecting them. To compute the total derivative, we need to add up the prediction errors from the layer below, scaled by the connection weights, and combine them with our earlier result. Notice that for some downstream neuron, if its activity is larger than its predicted value, to reduce the tension in the spring, we need to increase the prediction by moving the platform up, which can be done by moving the neuron at the layer above up as well, if the weight coupling them is positive. Conversely, if the prediction error is negative, tension can be decreased by lowering the predicted value through decreasing the activity of the upstream neuron. This elegant equation tells us something profound about neural dynamics. Activity is adjusted, trying to find a compromise between two competing influences. The first term drives the neuron to align with its top-down prediction, while the second term encourages it to better predict the layer below. When these forces settle into balance, the neuron has found its optimal activity level, one that minimizes prediction errors both at its own layer and the layer it helps to predict. But before we move to adjusting the weights, let's translate these update rules from abstract springs and platforms into actual neurons. Notice that each neuron must receive its own prediction error as input with a negative sign. Earlier, we treated this error as a kind of abstract subtraction, but this comparison must physically occur somewhere. We need a mechanism to store the prediction error so it can drive the activity changes. This is the fundamental insight of predictive coding. We need a separate population of neurons explicitly encoding prediction errors. In fact, this is the origin of the term predictive coding. Neurons forming a code that represents prediction errors rather than signals themselves. In our framework, within each layer, we can imagine that alongside each representational neuron x sub I, which encodes predictions passed to the layer below, there exists a dedicated error neuron, a biological counterpart that encodes the deviation of x sub I from its predicted value. With this structure in mind, we can directly read off the required neural connectivity from our update rule. A representational neuron x sub I must be inhibited by its corresponding error neuron and excited by error neurons sending feedback signals from the layer below. This elegantly maps our mathematical formulation onto biological circuitry. Now we need to determine what drives the error neurons themselves. By definition, error neurons function as comparators, calculating the difference between the activity of x sub I and its predicted value, which is given by the weighted combination of activities from the layer above. This equation reveals another set of required connections. Error neurons receive excitatory input from their partner representational neurons within the same layer, and inhibitory input from neurons in the layer above that communicate predictions. Perfect! Now we have two distinct populations of neurons, with specific excitatory and inhibitory connections between them. When allowed to unfold according to its own intrinsic dynamics, this network will settle into an equilibrium, which minimizes prediction errors across all layers. But everything we have discussed so far assumes fixed connection weights. To complete our model, we need to endow it with learning capabilities. Like neural activities, synaptic weights are also movable parts in our system that evolve towards configurations minimizing the total energy. For a weight connect to neuron I in layer L to neuron K in layer L-1, we can derive an update rule that decreases the total energy by taking steps opposite to the gradient direction. Since our energy function sums all squared prediction errors across the entire network, when we change the weight coupling those two neurons, the only term that is affected is the prediction error at the postsynaptic neuron. The derivative equals the negative of this prediction error multiplied by the presynaptic neuron's activity. This gives us an elegant update rule, where weight changes are proportional to the product of the two activities. This rule strikingly resembles Hebbian plasticity in neuroscience. Neurons that fire together wire together. However, translating this rule to biological neural connectivity reveals a challenge. Predictions flow from top to bottom, with the representational neuron I connecting to the neuron K at the layer below. When prediction errors flow upward, from this error neuron back to neuron I, our derivation requires using the same synaptic weight. But in biological networks, these are physically distinct synapses, and maintaining the perfect symmetry would require instantaneous communication between them, a phenomenon not observed in the brain. This so-called weight transport problem affects both backpropagation and predictive coding. However, closer examination of the weight dynamics suggests a possible resolution. For the two opposing synapses, the update rule is essentially identical, differing only in which neuron is presynaptic and which is postsynaptic. Consequently, feedback and feedforward synapses, which should theoretically match, may independently converge to similar values through similar update processes. In this way, the very physiology of the update naturally mitigates the weight transfer problem. I should note that in real models, though, there is a nonlinear activation function which we have been sweeping under the rug. When these nonlinearities are included, the updates for the two synapses are not mathematically identical. Fortunately, research suggests that perfect symmetry may not be essential. Even when feed-forward and feedback synapses learn independently with slightly different update rules, the approximate symmetry that emerges is sufficient for the network to function effectively. This learning rule integrates seamlessly with the activity dynamics we derived earlier. As neural activities settle to minimize prediction errors for specific inputs, the weights simultaneously adapt to encode statistical patterns across many experiences. Together, these processes enable the network to continuously refine its internal model, closely mimicking how biological neural circuits learn from experience. Let's now put everything together and see how this framework operates as a complete system. If we allow the network to freely adjust every parameter, both neural activities and the weights, it would naturally settle to a zero-energy state. However, this solution would be trivial and not perform any meaningful computation. In practical implementations of predictive coding, and likely in the brain itself, certain neurons are kind of clamped to specific values. The bottommost layer, for example, cannot vary freely since those neurons are directly driven by sensory input. This constraint forces the network to find an optimal compromise. When presented with a training example, the network undergoes an iterative relaxation process. Neural activities and weights adjust according to our local update rules until reaching an equilibrium configuration, an energy minimum that encodes information about the training example within the network structure. Repeating this process across diverse examples gradually refines the network's internal model of the world. Through this process, the network develops compressed representations of data. This can be leveraged for generative tasks, when we unclamp the output layer, freeze the weights, and let the network run to equilibrium to synthesize new images consistent with its learned model. For supervised learning tasks like classification, we also clamp the topmost layer to the desired label, allowing the network to discover optimal input-to-output mappings encoded in its connection weights. When classifying new inputs, we simply freeze the weights, let the system settle into equilibrium, and read off the label from the equilibrium activity of neurons at the top layer. The key advantage of predictive coding lies in its locality. While in backpropagation all adjustments serve this single goal of minimizing global output error, which must be transmitted throughout the entire network, in predictive coding, each neuron and synapse only responds to local prediction errors, how much a given layer deviates from its own prediction, and how well it predicts its neighbor. This biological plausibility and accordance with neurophysiological data, such as observed plasticity rules, suggest that predictive coding might very well be the key to understanding how our own brains learn so effectively. We can bring those insights into artificial intelligence as well. The local autonomy makes the algorithm extremely parallelizable, and in certain settings, more efficient than backpropagation. Theoretical considerations suggest that resulting updates may actually lead to better solutions than backpropagation. While Backprop focuses solely on the overall output loss, potentially overriding previously learned information, a phenomenon known as catastrophic forgetting, predictive coding's local update rules better preserve existing knowledge structure. To wrap up, let's summarize what we have explored today. By framing inference and learning as an energy minimization problem, where each layer predicts the activity of the layer below, we have derived an algorithm that operates with complete local autonomy. Unlike Backprop, which requires global coordination and separate phases for computation and learning, predictive coding emerges as a continuous, parallel process, where neurons simultaneously predict, compare, and adapt. This approach not only aligns with the biological constraints of neural tissue, but potentially offers computational advantages for artificial models. As neuroscience and artificial intelligence continue to inform each other, predictive coding stands as a compelling bridge between the remarkable learning capabilities of biological brains and the next generation of neural network architectures. Speaking of efficient learning, if you would like to gain a deeper understanding of the foundational concepts behind today's ideas, you are going to love our today's sponsor, Brilliant.org. Brilliant helps you master STEM topics by combining interactive visualizations with hands-on problem-solving. Their engaging courses allow you to learn by doing and build intuition, breaking down challenging concepts into bite-sized lessons. Especially relevant to this video is their course titled Introduction to Neural Networks, which builds up from the definition of an artificial neuron to hidden layers and activation functions, giving you practical experience with the building blocks we discussed. Brilliant offers a great collection of courses across mathematics, physics, and computer science. Whether you are a beginner building core knowledge or an expert exploring new domains, Brilliant has something for everyone. If you're ready to take your learning to the next level, head to brilliant.org/Artem to get a 30-day free trial of everything Brilliant has to offer, plus a 20% discount on annual subscription. If you liked the video, share it with your friends, subscribe to the channel if you haven't already, and press the like button. Stay tuned for more neuroscience and machine learning topics coming up.